So we've talked about dark matter and a little bit about dark energy, and we've talked about our accelerating universe, the fact that the fabric of space-time within our universe is getting larger and larger. It's expanding at an accelerated rate. And now we're going to talk about kind of the Big Bang Theory, and bringing it up to kind of where we are today. So this is a pretty good little animation I think I'm going to show you. And one of the things on the next few slides I'm going to hit heavy is the fact that our universe, the way it is now, as we go back in time towards the Big Bang, or at the time of the Big Bang itself, our universe is a lot hotter and a lot denser. So let me kind of play this to highlight that. Maybe. So it's not real fancy. So these little things that look like little rodent turds are actually galaxies. And so we're going back in time. So if it's expanding now, going back in time, it would be contracting. So it's contracting, getting more and more dense. Okay. And actually, if we date the Big Bang at being 13.7 billion years ago, this goes back even further than that. So, all right. So if we were to plot the time versus temperature of our universe, that's what this line does. So our universe cooled down very quickly early on, because I want to kind of highlight the time is along the x-axis from left to right. Time is increasing, but notice this right here, it's not linear. It's like by base 10 it looks like. This is 1 second after the Big Bang. So here we go, just to kind of highlight some things. So this is back a fraction of a second, actually 10 to the negative 35 seconds. Okay, and this would be the corresponding temperature. This temperature here would correspond to, for instance, this 10 raised to the 28th. Now this is temperature in the Kelvin scale, so that would be a 1 with 28 zeros after it. Okay, Kelvin units. So what this line says is that from left to right, time is increasing, although we have 1 second finally here. And notice that the universe is cooling down. It's cooling down actually kind of related to as it expands. So here we have actually 4 times 10 raised to the 17th power, so 4 with 17 zeros after it. That number of seconds actually brings us up to about 4.7 or 4.6 billion years after the Big Bang. Does that make sense? So this 10 to the 15th, a little bit to the right of it, that is present day. So we've cooled down quite a bit. Specifically, if you were to take the temperature, gauge the temperature of our universe, we're running about 3 Kelvin now. But I'm warning you, that's pretty darn cold, because on the Kelvin scale, typical temperatures, like surface temperatures, runs about 298 Kelvin. So 3 Kelvin is very cold for the universe compared to our toasty spot here on Earth. So we're going to talk about eras. We're going to break the unfolding of our universe, is the way I like to think of it. The creation of our universe from the Big Bang, the fabric of space-time was created, and it's been expanding ever since. We're going to talk about it in terms of eras, kind of break it up into chunks of what happened here or there, that sort of thing. But early on, like right at the time of the Big Bang, matter and energy were converting back and forth between each other. And actually these two slides, if you read it kind of from left to right, in this case we have energy converting to matter. In this case we have matter converting to energy. So that's the sort of chaos that was going on at the very initial time, I guess I should say, of our universe. And Einstein actually says that this conversion can happen, and we actually know this conversion to happen in nuclear fusion or fission reactions. A small amount of matter is created into, or is converted into, a large amount of energy. So this is a pretty good slide. This kind of, from the upper left to the lower right, is showing you, well, a little bit about kind of the eras. You're starting to kind of get a hint for something major happened at that little number up there is 380,000 years. Something important happened 380,000 years after the Big Bang. But I'm just going to warn you that a lot of important things happened between the Big Bang and that time. And so this kind of shows you a little bit our universe expanding. It cooled down, so as it expanded, its density became less, and expansion also resulted in a cooling, because it had to cool down sufficient to actually finally get atoms to form, and then it finally had to cool down to get those atoms to form into molecules or compounds. I guess molecules first. Okay. So, when we talk about these eras, we're going to talk about two important aspects of these eras. One of them is what sort of forces were present at that particular time in the history of the universe. And the other is what kind of particles were present at that point in the universe. Okay, and remember, the universe started out as very, very, very dense, oh my goodness, crazy dense, and very, 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 very hot, crazy hot. And it has been expanding, so its density has been decreasing and been cooling down ever since. So the four forces we need to talk about actually are the four fundamental forces that are with us today. And as I put these up here, though, I'm going to warn you that our universe historically has not had these four separate forces. The first two might be something that you are very familiar with. Gravity, for instance. Well, that's one of the four fundamental forces in our universe. The other one is electromagnetic force. An example of that is something positive and something negative, positive particle and negative particle. Actually, there is a force of an attraction between these two particles. That's the electromagnetic force. The weak force and the strong force then both have to kind of do more with the atom itself. Remember, all matter, all normal matter, is made up of atoms. And weak force is associated with radioactive decay, and strong force, though, is associated with regular old atoms minding their own business. And remember the structure of an atom we talked about earlier in this class, that atoms are composed of a nucleus, and the nucleus has neutrons and protons in the nucleus. And as I said a minute ago, protons positively charged and electrons would have an attraction for each other. Well, protons and protons in the nucleus of an atom have a repulsion for each other. So it's this strong force that holds the nuclei of all of the atoms that are in our universe together. Strong force, pretty darn strong. So with regard to those four forces, we could look back in time, and I think I mentioned that those four forces, the strong force, well, we first started out with gravity, the force of gravity, the electromagnetic force, the strong force, and the weak force, they weren't always present in our universe. So the way we read this, this chart, or the graph, with regard to the forces that were present over these at particular time, we need to know now that the x-axis is switched from what we looked at it before. So time is increasing from right back to left again. So actually, as it works out, time over here is still less than a second, less than 1 second after the Big Bang. Is that crazy or what? Okay, now also along the x-axis, from left to right, we can see decreasing temperatures, see the universe cooling off. So then along the y-axis, these four forces, along the y-axis is going to indicate the strength of each of these four forces. And so actually these four forces today, and these four forces actually maybe less than 1 second after the Big Bang, were separate. You see down here we have the force of gravity relatively low. We have the weak force, the electromagnetic force, and the strong force. Okay, and they're kind of relative strengths. Well, you go back like 10 to the negative 10th seconds after the Big Bang, and we start to see some forces combine. Specifically, we start to see the electromagnetic force and the weak force combine to make what we call an electroweak force. The strong force wasn't as strong as it is now, and notice that the force of gravity was stronger back here. Looks like we're looking at 10 to the negative 38th seconds. 10 to the negative 38th of 1 second after the Big Bang. Is that cool or what? Okay. So moving back even further then, we see that the strong force joins in with the electroweak force. So those three forces join together. That would be the strong force, the electromagnetic force, and the weak force. When they join together here, they were joined together, I guess I should say, shortly after the Big Bang, they're called the gut force. Notice that the force of gravity was really was a lot stronger than it is today, back here at the time of the Big Bang. So there is work actually in maybe those, all four forces were unified at the time of the Big Bang. So do forces tend to unify at higher temperatures? Well, we saw that at the higher temperatures shortly after the Big Bang, we saw back somewhere in the vicinity of 10 to the negative 10th seconds that the electromagnetic and the weak force joined together to make the electroweak force. We saw at even hotter temperatures and more dense of a universe, we saw that the three forces, strong force, electromagnetic force, and weak force, joined together in what we call the gut force. And perhaps way back shortly at the unfolding of space and time of our universe, maybe gravity was thrown in there with the other three forces. And string theory might kind of ultimately lay some